Welcome everyone, and thank you for joining us today. I'm Bengi Zeybek. I'm a PhD researcher at the University of Amsterdam, and I'm very happy to be moderating this panel today about privacy and surveillance in the quantum age, developments on quantum sensing technologies and their implications. Before introducing the panelists, I just want to give a brief background on the topic of the panel, and then I'll quickly introduce the panelists, and after the presentations of the panelists, we'll turn back to the audience for some questions. When you look at quantum innovation landscape, sensing technologies are a bit the odd ones out. They get relatively less attention compared to quantum computers or quantum communications. But actually, quantum sensing technologies have a relatively higher technology readiness level and actually wider possible application areas that range from defense, biomedicine, space, environmental science, and mining, and so on. And we already actually have some experience with quantum sensing technologies, the early ones like the MRI or the GPS. And at the moment, most quantum sensing technologies are being tested in lab environments, and it's really not so easy to predict how and where they will be adopted. And also, mostly the research and development is concentrated in defense and military. But actually, once realized, these sensors could facilitate the capture of more data points than that is possible with traditional devices, and they could enhance information processing infrastructures, like, for example, seeing through walls, detecting objects out of sight, sensing materials underground could be possible with quantum sensing technologies. Like, it kind of sounds like science fiction, actually. And in the end, quantum sensors could effectively transform surveillance and data gathering practices of intelligence, law enforcement, and commercial entities. And the question is then, what could this mean for privacy? And motivated by this question, this panel is meant to introduce quantum sensing technologies to privacy and broader technology policy community, and to provide an early exploration of some of the essential topics in this issue. And to do so, we have a phenomenal panel here with us today. I'll just introduce them very quickly in the order in which they will speak. To the left of me, the first speaker is Philippe Bouillet. He's a French physicist, and he's a board member of Quantum Delta NL and the director of research and technology. He's a professor at the University of Amsterdam and also the Technical University of Eindhoven. And he'll talk about what quantum sensing technologies are and some of their potential applications. And to the left of Philip, we have Henning Soler joining us today. He's a partner at McKinsey & Company, and he's leading research on quantum technologies and helping financial industries overcome legacy obstacles. He is the co-author of 3 McKinsey research reports. They're called Quantum Technology Monitor, and they map the investment landscape on quantum technologies, including quantum sensing. And he'll contribute with explanations on notable developments and key actors in the quantum space. And to the left of Henning, we have Chris J. Hofnagel. He's a professor in law in residence at the University of California, Berkeley, and visiting scholar, King's College of War Studies. He'll talk about main privacy law and policy implications of quantum sensing and how the law could respond to their dual-use nature. And the last speaker is, last but not least, Masha Galjic, and she's an assistant professor in privacy and criminal procedure law at the Criminal Law Department of the Vrije Universiteit in Amsterdam. And she'll bring privacy law and surveillance studies perspectives to this discussion. And with that, I'll give the floor to Philip. Thank you.
Well, thank you very much for the introduction, and thank you. I'm very honored to be in this very exciting panel. So I have the duty of introducing quantum sensing to you. So I will not give you a lecture on quantum mechanics, but Well, the first thing is, well, you all know about the nice pictures you see on quantum computers, especially the superconducting quantum computers. You have this big fridge with these nice wires, and basically the qubit inside this fridge, it's a tiny piece of chip there. The rest of the equipment, the big chunk of like metal and also superfluid helium and etc., is here to protect the qubit to its environment, because a quantum system, the qubit, is very fragile. It's very sensitive to what happens around him. So you need to isolate him if you want to make calculations. Quantum sensing, it's actually exactly the reverse. We want to take advantage of the fact that a qubit, a quantum system, is very fragile. It's very fragile, which means that anything that can happen around it can be sensed by this quantum object, and then if we can read out what's happening to this quantum object, then we can have a very sensitive way of measuring things. So before like maybe introducing different types or like the application of quantum sensing, I just also want to introduce what is sensing and what is very important when you are speaking about sensing. I give a very simple example. If you want to measure your weight, you step on a scale, and basically you convert your weight into a number. This number is either like a tiny scale which is moving around, or it's a number which is like some digits on the scale itself. That's because you have a process, sometimes it's a spring or it's an electromagnetic system, that is basically converting weight into these numbers that you can use then for like first like being happy if you're like lighter, or being depressed if you have more weight. But the fact is, the number you have, it's not exactly an exact transcription of your weight. You need, and very often we speak about calibrating a sensor, which means that you don't know exactly what's happening, because the spring, like one spring will not be the same as another one. One electronic system will not be exactly the same as another one. So you need to have this calibration in order to say, well, this number corresponds to my weight. And maybe it's not true 2 days after, so you need to recalibrate it again. So that's where a quantum system is actually making a difference, because if now I want to measure my weight with a quantum system, I can use a single atom, and if I'm close to these atoms, gravity tells me that the atoms will be affected. It will be attracted to me. It's the universal attraction of different objects. If I can measure how attracted this atom is to me, then I can measure my weight in a certain way. And this is just ruled by the laws of physics. So that's exact laws that I can calculate, and I can, in that case, exactly know what is the number I can read out from my sensor by just like looking at the effect of this, of my weight on the atom itself. So that's how I can measure weight. Basically, there is currently a quantum sensor, which is, we call it measuring gravity. Gravity is just the number that gives that corresponds to the attraction. By just looking at how an atom is affected, an atom at very low temperature, it's a quantum system, it's a qubit, and if this qubit is affected, then I can measure how affected it is. It is very sensitive. I mean, these quantum gravimeters, we call them, can measure gravity at a level of 10 to the minus 9. So that's, gravity is 9.8 meters per second squared, roughly 10 meters per second squared that you learn at school, but now I'm measuring 9.8 with 90 behind it. It's so sensitive that if I change, basically, if I move by 1 millimeter up, my weight is changing by 10 minus 9. So my weight is changing because gravity is changing. My weight is just how my density is actually converted into universal attraction to the Earth. So I can measure so precisely that I could feel with a quantum sensor a difference of 1 millimeter. This is the best way of measuring height, for instance. Like you mentioned GPS. GPS is also using quantum clocks, and GPS can measure, the best GPS ever can measure height difference at the level of a centimeter. The GPS you have on your phone will measure it at the level of a meter or more. So this is telling you the difference. Why is it so useful? Maybe not to know if you are lighter or not lighter, or maybe not to know if you are like 1 millimeter up or not up, but the thing is, your atom is far away from you, so it can measure weight without actually you needed to touch it. You needed to be connected to it. So if I want now to, for example, measure the weight of a truck, the way it's done today, the truck has to stop on a scale, then you measure the weight of the truck, and then the truck goes away. But you need to, as I said before, to recalibrate the scale in order to be sure that the next truck will have the same weight, etc., etc. Now, if I put my atom close to the truck, then the truck drives by, and I know exactly what's in the truck. If the truck is empty, or if the truck is full. You talked about like military applications. I can know whether the truck is transporting normal material, maybe food or something, or very dense material, like radioactive material, for instance. So that's some kind of application of this weight measurement, very sensitive measurement. There are many other things you can do. You can look through the, like you can watch through the walls, or you can watch below your feet without the need to dig. You can actually monitor gravity very precisely without having to, and then you can look at whether there is a cavity on the ground or whether there is a change of density that corresponds to different materials. So this is good for resource management, but this is also good to look at hidden places. So that's one example of a quantum sensor. It's good because it's sensitive, as I said before. It's good because you don't need to calibrate it because physics is actually ruling how it works. And because of these two reasons, it's also good because you can put a sensor somewhere and it will work all the time over many, many years, giving you the same result if there is no change. And if you change it, if something changes around, then the sensor will tell you something changed. Why can you use that? Again, if I only refer to gravity, I'll come back to other examples. If I put my sensors close to a volcano, and this is an application which is actually happening now, there is a quantum sensor on the top of the Etna in Italy, just to look whether there is a magma coming or not coming. And you can feel with these quantum sensors magma mass of something like 1,000 tons or 10,000 tons. That sounds big, but it is actually the level of magma fluctuation you have in a volcano without having to go inside the volcano, which is impossible. So this is the only way, feeling away from where you want to measure the things with a very precise and sensitive sensor. This is the only way you can predict eruptions, for instance. And you could do the same to predict earthquakes or things like this. So this is the kind of applications you can do with a quantum sensor. So of course I gave a very precise example, which is a quantum gravimeter, as we call it, something which is measuring the change of weight, the change of density, the change of gravity, far away from where it wants to measure it. But you can use quantum sensors in many other ways. You can measure electromagnetic fields. So for example, you can have very sensitive radio antennas that are using quantum sensors. You can detect tiny radioelectric signals. So you could detect tiny radio transmissions, for instance, that could be very fake if you don't have this type of detection capacity. And again, because it's stable in time, you could see, oh, there is a radio communication where there was no radio communication the day before. And I'm sure it is not noise, it's just because my sensor is working very well. You can detect extremely precisely magnetic fields, and that leads to many health care applications. For instance, you can look at your heartbeat. So usually heartbeat is now monitored using electric fields. You know, it's electrocardiogram, but you can use magnetocardiogram, and you can make a magnetic map of your heartbeat inside your body. You can put many sensors around your body, and then you can see how basically the beat is, how your heartbeat is, but also how this heartbeat or how the flow of blood is actually different in your arms, in your feet, in your body, and etc. That has a lot of implications. You can use magnetic field to monitor your brain. You can make a brain, like a magnetic map of your brain with bazillions of sensors, and again, you can really, so this can be used for health, of course for health, but it also can be used to make some new interface, like communication, you know, a brain interface to like something that I felt looked like science fiction, but it can happen today in a certain way. And again, it's so sensitive and so reliable in the sense that you know that if something is seen, it's not an artifact, at least not from the sensor, because the sensor is well known. So that's the type of applications you can use. You can also measure pressure very precisely. You can measure temperature very precisely. So that's what a quantum sensor can do, and they're all based on qubits. So they can be atomic qubits, they can be other type of qubits using light, photonic qubits. They can be qubits using superconducting circuits, a little bit like the superconducting computers. They can measure magnetic field very precisely. You can use what we call NV centers. That's also tiny pieces of diamond that have been actually engineered in the way that they behave like a quantum system, and you know exactly what's happening there. So the concept of a quantum sensor is more or less always the same. It's just like for different type of applications, for different type of sensitivity you're looking at, from different type of like quantity you want to measure, you will use a certain type or a certain family of qubits, and for others you will use another type of family of qubits. So that's, let's say in a nutshell, what is a quantum sensor and why, I mean, I've been excited for 30 years working on that. And I hope you will be excited to work for the next 30 years as well. So if now it's, what are the challenges in, well, there are many challenges. So the first challenge is I spoke a lot about what you can do with it. Like I can measure this, I can measure that. But of course, if you want to measure something, that means that you need to convert these very nice concepts, these very nice experiments, if you go to labs, into something that is quite practical. I want to put a sensor on the top of the Etna, and believe me, it's not easy because this is like very far from where you can actually apply very precise measurement. There is change of temperature, there is change of pressure. Sometimes you cannot go there because there is an eruption, etc. So you need to actually then tackle how you can convert this very nice physical concept into something practical that can be operated by anybody in a certain way. And then the challenge is going from...
Sorry for interrupting you, but we are way over time.
Okay, so yeah. So that's the type of challenges that we are today. There are some examples of quantum sensors. There are some quantum sensors that are being seen also to change for navigations and position. But yeah, so I will stop now and maybe
despite the fact that we're very over time, sort of one quick question from my side. Do you see some of the technologies that will win at the end and some technologies where you have less belief, or how do you see the landscape at the moment?
So just very briefly, I think it really depends the type of applications you have. So we are at a stage where we can go to the market with this type of sensors. Some are already quite tiny and deployable in mass, like these small NV centers, for instance, that are used for heads. So they are very good for this type of things. Also, the price is lower, so for this deployment, it's important. In terms of higher sensitivity, like atoms are also very good, but then they are more expensive, so they can be applied to other type of markets. So I think depending on the use case, you will have a different technology choice to make, and then a deployment of different technology of quantum sensors.
Thank you. Great. Thank you so much. Thanks. Great insight on the value of measurement and how quantum sensors can be extremely precise and how they're also useful for real world problems as well. So I give the floor to Henning.
Sure, very happy to. And sort of don't worry, sort of we'll get ourselves back in time. There is this wonderful note here, sort of 1 minute left, so I'll hope I'll stick to the time this time. Because I remember sort of Nancy Reagan once told to the consultants of Ronald Reagan in front of his presidential campaign, "Don't confuse my husband with too much information, he cannot handle it." So let me hope for the best. Second is sort of course, feel quite honored sort of also by the massive presence that we see today. So I thought sort of I'm very lucky if 20 people will come. I think this is extremely cool to see also the amount of interest that we see and the amount of time that you're willing to spend with us. Third is when this morning I also looked at the motto also for CPDP. I thought it's actually a nice thing sort of also where we currently stand in terms of the economic development on the quantum sensing side, because it's exactly the question. We're now moving from something that was previously purely physics research to something that is now taken to an actual economic application. And the question is exactly one of those. Are we now governed, or sort of can we govern this thing by ourselves? And this is also why I got particularly interested in this topic in the first place, because I think this is one of the few possibilities also where physicists can now take the respective technology and actually put it into practical use. which I've seen sort of in the days when I was a theoretical physicist, is almost like selling your soul to the devil. But I think this is actually the possibility of also now making sure that the technology gets into actual usage, and that we can also take advantage of sort of new pools and new ways of working that are also enabled through this new age that we have. Because what I see, and sort of this is not just confined to quantum sensing, but specifically also on the quantum sensing side, is through the advent of PE money, VC money, essentially coming into the space. We've seen a lot of professionalization of the corresponding enterprises, a lot more also intrinsically driven cooperation with corporates and with larger companies, which essentially is leading to, okay, let's overcome the phase of we do R&D on an ongoing basis and we really identify where we can put the respective technology to use. Let me also give you a few numbers, and sort of the quantum monitor was mentioned already as one of the sources where we've gathered a lot of the information as well. Is we've seen so far roughly sort of 8.5 billion in terms of investments into quantum technology, and sort of few caveats around this. We have almost zero transparency on how much was invested on the Chinese side. So if anyone knows, please tell me. Second is, this is a rough estimate because it's also a bit of a shade of gray, sort of what is now a quantum company, what is not a quantum company. Do we calculate something like post-quantum cryptography as something that is quantum or not? Big question mark. But sort of roughly that is the number that we have, which is not super massive as something that you would see in terms of Gen AI currently, but it's sizable in terms of the actual investment that now has been put behind, which also tells you there is a lot of confidence also at the VC and PE level that there is something that we now have that can actually be put into economical usage, which is cool because in the days when I was a PhD, sort of everyone was dreaming about the actual economic usage of those things. Second is we've also looked at what is the actual possibility in terms of the market size, both in terms of the sensing side, as well as also what we see on the overall quantum technology side. And sort of what we overall see on the quantum technology side is roughly we're looking at until 2035, 2040, of course, depending on how the technology would also evolve, at something like a $90 to $100 billion market in terms of the actual technology solutions behind that. And that is sizable. I mean, it's not yet the total number of the revenues of Google and Amazon and so on combined, but it's a sizable size of the overall technology market. And the second thing that is important around this is the actual impact that this could have also on the overall economy is massive, because we've done also a bottom-up estimation of what are the use cases that you would also have. And roughly what we see is that there is a possibility of enabling roughly 900 billion to $2 trillion in terms of actual impact, and also at the industry, depending on what is the final maturity also of the underlying technology. I think this number will even rise further because we will see more identification also of additional use cases in terms of where can we put this respective technology also to use. And just to go a bit sort of also into the quantum sensing side, so also for quantum sensing alone, we will at least see a $10 billion market that will be emerging until 2035. And we've already seen 700 million in terms of investment also into the quantum sensing startups and the respective companies around that. So there is a sizable opportunity, and as was already mentioned, quantum sensing is a bit different to quantum computing, because on quantum computing we don't yet have a product that we can actually sell, if we're honest to ourselves. On quantum sensing we have a product that we can actually sell. In many, many cases these sensors actually work. And that is one of the aspects that is really cool to see. Just to present also the picture in terms of what are some of the recent developments. We've also seen that recently there has been, of course, a slowdown in terms of the actual investments by PE and VC funds. There has been also a drop of around 27% in terms of the investments from 2022 to 2023 into the respective sensing startups. But this is still smaller than the overall drop that we have seen also in terms of startup investments that we've seen over the last few years. And then I think we've already talked a lot about the commercialization of the respective technologies. So specifically we see that imaging, monitoring, navigation, also identification, as we said, sort of materials, sort of are the key use cases that we also see in the industry. And we also see the possibilities of very widespread application, not just on the military side, but specifically also on the healthcare side, we will possibly see a lot more applications that are currently already in the making in terms of what we could actually do also with car makers on the respective application of those technologies. Also, given that we now see that these technologies can be put into use also in environments that are not as well controlled as you would have, for example, if you use them in healthcare applications where typically you have a more controlled environment in the first place. What I think is the final thing that I just wanted to mention around this is we see that a lot of the players at this point in time are around the technologies of the quantum diamonds and the NV centers, simply because by now, sort of quite reliably, we can produce these things, and they are also actually working, and we see the same essentially also on the superconducting qubits. Despite the fact that many people have always said sort of it's a legacy technology, it has certain deficiencies for sure, but we see that it actually works, which is cool. And sort of this is the contrast also to some of the quantum computers. So I think that's important to mention. We also see like other things like plasmonic sensors and others are in the making, and we will also see their advent also in the market. Final aspect that I would like to mention around this is what we've not yet seen, but what we will possibly also see is that this will actually go also into the development of actual ecosystems, because the real application of the more traditional sensors and the real cool impact that we've seen from those essentially came from the fact that we were able to combine the different sensor data and then to also make actual algorithms on top of the respective sensor data that we have gotten. We're still at the real beginning in terms of creating these ecosystems. We don't yet have interface standards. These things have all kinds of data outputs. You already mentioned around the calibration of the sensors. It's a nightmare at this point in time. We believe that there is a lot of stuff that will need to happen, but also there is a lot of additional impact that we will be able to see from the actual combination of those sensors then also in a combined ecosystem. And with this, would love to close here.
Thank you, Henning. Great insights. And I was wondering if any of the panelists would like to respond or react to Henning's comments.
If it's
Sure.
okay.
Yeah,
It's extremely useful to hear your market projections. That information is very hard to come by. How do you, as an analyst, distinguish between the kind of marketing hype, the fluff that's out there, and what you think is really promising?
Love the question, because sort of the differentiation is not easy to do, but sort of the way that we essentially wanted to run this was that we essentially had based our estimations in terms of what we see in terms of the possible impact also on actual use cases, so that we can basically say, okay, if we do this differently, what is the impact? What kind of effect will this also have on the overall industry? What we have done to quite some degree, but what is difficult is the actual benchmarking also of the underlying technologies, like really looking at how do the different qubits work and what is actual reality in terms of the underlying qubits. To be honest, with some of the emerging technologies, I mean, every one of you will have heard about the Majorana fermions. The information that is really reliable that we could have on those kinds of things that you could really put into an investor report is limited, to say the least, questionable to also say the least. So that is sort of how we try to address this. Have we overcome the challenge that you mentioned? For sure, the answer is no. Would just like to mention one more thing. We've also seen, and sort of at least in every second call at McKinsey, sort of that I get in, sort of when it's like, hey, sort of Henning is our guy on quantum, everyone says, okay, like this will never see the light. That is the other thing that we need to overcome. I think there is a lot of marketing hype, and sort of also because of the past experience, there is a lot of disbelief that this technology will actually work at the end. And I think what we always need to make sure is to say specifically on quantum sensing, like, look, this is simply not true. This technology is working today. Like you can see it. You can have the sensor right away. I think that's important just to say, also and overcome this criticism that has been around, because technology for 20 years needed to have quite some life cycle to undergo in terms of reaching maturity.
Thank you. And another thing to add to that, you mentioned that, so the technology is working, but does it actually speak to a need, or how are these needs constructed when you have the technology? But how are the problems that it speaks to constructed?
So The challenge at the moment is we don't know sort of what are all the possible problems that this thing can solve. This is also why I said the projections in terms of the impact will even go up. So currently we assume quantum will have roughly the same impact as Gen AI. I think this answer that I just gave is wrong because we've not yet discovered all the use cases. At the moment, we basically work with, okay, we have a use case where we know that this thing can work because, for example, magnetic field measurement, we know magnetic resonance tomography. If we can do better magnetic field measurements, we'll get to higher higher precision on the measurement. This will allow us to do better results, for example, in terms of identifying a tumor and then sort of also to do the corresponding therapy of the tumor. These are use cases that we have. And so with several of the corporates, we have essentially worked on that basis in terms of, okay, we've identified the problem, we've identified there is a quantum sensor, we can put a solution there. That is the ongoing research that we need to go through because just to tell you, to be also open, like originally we estimated impact of quantum in the financial services industry was 300 billion. Last year, sort of when we dig deeper, the number went up and sort of everyone will have seen it in our monitor to 600 billion simply because we discovered a lot of additional use cases that were previously not discovered. So that is an exercise that we need to go through.
Thank you so much. Chris, please, go ahead.
Thanks so much. Thank you, Bengi, for organizing this panel. I wrote a book on this topic. It's called The Quantum Age. It's an open access book, so it's free for you to download. So don't buy it. You can just download it from the Cambridge University Press website. I wrote that book with Simpson Garfinkel, who I think is known to many people at CPDP. We have different training and different areas of expertise that shed light on the area. And if you look at the book, you'll see that it has an appendix that has a basic science introduction to quantum technologies, but then the main part of the book is functional. It only discusses quantum sensing and computing and communication through their functional elements. So the main part of the book can be understood by a policymaker with no background. And I'm delighted to be part of this panel because the thesis of the book very much aligns with the theory of this panel. And that is that quantum sensing is here. There's fielded technology. There's quantum sensing on the International Space Station. There are companies that are making these devices, and they are being installed in weapons and other systems to deal with PNT, positioning, navigation, and timing. I think Philippe didn't have enough time to fully explain that, but it's to deal with the GPS problems that we're experiencing. So these things are out there. And I think quantum sensing and a related technology short of quantum computing called quantum simulation is another field that really needs to be paid attention to now. That's going to be real in the near term. It has profound implications for civil liberties and privacy. And this is I want to steer this community away from concerns about cryptanalysis in quantum computing. Simpson and I have a separate standalone article in Lawfare that explains why the cryptanalysis threat is overhyped. And we do it from both a technical and operational viewpoint. Simpson is a longtime employee of the intelligence community, and he knows how decryption works. So we explain why the cryptanalysis attacks are not a near-term threat, and how they will actually manifest, which is different than many people say. So the manifestation, if they do manifest, could be quite shocking. But the way they will manifest is not obvious. So for this audience, because CPDP is a group very attuned to civil liberties and privacy issues, I just wanted to mention a couple high-level themes. I'm really happy that Philippe began his presentation by talking about quantum sensing and gravity, because that is the area that really we need to think about from a privacy standpoint, because we can't do this sensing right now. It's in fact, it's kind of out of our mental models for privacy. So the types of things that I think this community should think about are whether quantum sensing enables more resolution. That's a class of problem. That's a class of problem that has to be thought about. But the other class of problem to think about are new capabilities. And so what Philippe talked about were some new capabilities that challenge our models for privacy protection. One is remote sensing. So the ability to sense, for instance, the weight is does this truck carry a bomb or does this truck carry flour from a distance is important. Because we can think about notice and other hallmarks of fairness usually require interaction with the sensor, interaction with someone who's trying to measure you. But remote sensing changes that. A lot of quantum sensing can be done in space. So that is another thing, another aspect to think about, that there could be measurement, understanding of the world that is completely opaque to people. Another new capability that's important to think about is stealth sensing. This is in part a category of remote sensing, but one of the things that some quantum sensors do is enable a party to sense without the counterparty being able to discover that sensing. So the paradigmatic example of this is quantum radar. It's a photonic-based sensing to defeat low observables, stealth aircraft. What I think is most interesting about it is that if this technology works, a government could set up a quantum radar array that could not be detectable by the adversary. This is a very important dynamic. It's not well understood, but a lot of what nation-state conflict is about is finding radar. And if you can have radar that can't be sensed, that is a real game changer. It's strategically significant. Another important aspect of quantum sensing is its use in denied environments. So you might have read in the Financial Times that Russia and a couple other nations are extensively using GPS denial. It's really easy to block GPS. You can buy $10, $20 devices that will create local GPS jamming. Nations have mastered it on a much wider level. And so one thing that's driving quantum sensing is the ability to have a device that won't be affected by GPS denial or other type of electronic warfare. Really important with respect to both Russia and China. So one of the things my center has worked up is the reality that nations like Taiwan have a single quantum clock in their nation. And so in a conflict with China, that quantum clock could be one of the first targets that China might choose. And so then the question becomes, can you find other forms of time measurement that can be distributed on Taiwan so that computers don't drift, so that you can have accurate computing even in a conflict. And then finally, the last big capabilities change that I think we need to think about is that many people in the privacy and civil liberties community, when they think about intelligence surveillance, they think about signals intelligence. And this is because of Edward Snowden and some other people, big focus on signals. There are entirely different classes of intelligence that benefit from sensing. The field is known as massent, measurement, and signature intelligence. One of the predictions that Simpson and I make in our book is that massent, the types of sensing that Philippe began to give us a picture of, will actually become more important than signals intelligence. It's going to become very difficult for nation states to hide things in an environment where there's quantum sensing, especially paired with space capabilities. So nations might spy on people in the future by detecting their presence, detecting what's in their cars, and so on, rather than trying to decode what their signals mean. And then finally, countermeasures are important. And I'm hoping that maybe our conversation will elicit some of this. I'm not really sure what the countermeasures are. How do we have an idea of, like, if someone wants to look through my window, my countermeasure is I can put down my blinds, or I can have law that says you're not allowed to point a camera into a bedroom. What do countermeasures look like when a nation can sense gravity? I think that's it's a key question we have to start thinking about.
Thank you so much, Chris. And I have some questions, but I will ask them after Masha's input as well.
Okay, thanks, Bengi. Thank you, Chris. So today, Bengi asked me to give a surveillance studies perspective on advanced sensing technologies. So as you can see, I won't specifically talk about quantum sensing. I'll talk about a broader notion of advanced sensing technologies, and I'll tell you why I do this in a moment. And I call my presentation, or I'll talk about what I call sensory power. So obviously, we're here at CPDP and not at Surveillance and Society, which is a conference in Ljubljana, Slovenia next week, which I'll be. So I'll give you a very brief introduction into surveillance studies to begin with. So what this is, it's a relatively new, but not so new, a field. It's a multidisciplinary field which covers theoretical and empirical accounts of past, current, and near future surveillance in society. And it's really a mix of different disciplines. It starts off with sociology, political science, media studies, of course law, I'm a lawyer, criminology, anthropology, and war studies. Obviously you hear how this ties in with Chris's presentation. And basically, in a nutshell, to make it really simple, what surveillance studies do, they study how surveillance affects power relations in society. And what I mean by power here, I understand it in a Foucauldian sense as strategies and technologies through which people govern the behavior of themselves and, of course, of others. So that's why it's important to really indeed see, as Bengi says, or to look at how these new quantum technologies will affect existing surveillance techniques in a society, between people, but also, I think, primarily between nation states. And how surveillance studies does this, how does it study these power relations? It asks critical questions, such as who conducts the surveillance? Is it primarily state actors? Is it private actors? Is it individuals themselves? And who or what is under surveillance? And that's an important one in this case of advanced sensors. What is the purpose of this surveillance? Again, the answer to this question can be many different things. And most importantly, and this is what I'll focus on today, how is this power exercised? What is the logic of surveillance? Surveillance can come in many shapes and sizes. Most people think of a Big Brother scenario or the panopticon, but actually there are different types of operating logics of surveillance, how this actually happens. And through sensors, technologies such as sensors is one way of surveillance taking place. And this is where we come to the topic of advanced sensing technologies. And quantum sensing technologies are a type of form of advanced sensors. We heard today that they are an important breakthrough, and I'm not here to deny this, but I do want to problematize Bengi's question, will quantum sensing technologies transform surveillance? I'm not so sure, or at least not in the day-to-day lives of people. Maybe more in the military context, maybe specifically in the medical context and in relations between nation states, but not really in my or your day-to-day life. Because quantum sensing technologies, they just tie into the existing wide array of advanced sensors that we can see both in our homes and especially also in public spaces. So at home, we have now a lot of smart sensors. I'm away from my home. My smart camera is protecting my property. We have baby monitors. We have our smartphones, which have a bunch of sensors on them, potentially. And if you think about smart cities, we have a lot of sensors that are embedded into public space itself. So not just the usual old CCTV cameras, we have advanced cameras with analytical capabilities. We have sound sensors and sound cameras that can pinpoint the location of a particular sound. We have advanced lighting technologies that can adapt to what the atmosphere on the street. So we have all types of sensors, And we can see how certain types of quantum sensing technologies could tie into this. And also perhaps at the level of law enforcement investigation, they might help law enforcement indeed to surveil from a distance and in an obscure way, in a stealthy manner. But that's already something that can already be done. We can already see through walls, right, with infrared technology. And we can already see from a large distance and in a very stealthy way. So what quantum sensing here does is, yes, it makes potentially additional things measurable because it measures at an atomic or even subatomic level. And it makes things measurable in another way, from a longer distance with more precision, more stealthily. But all of these things also already exist. So that is how we need to think about them. So if we think about this question, how is power now exercised, we need to think a little bit more, okay, what kind of surveillance are we dealing with here? And that's a key question. And because we're dealing with sensors, we are clearly talking about what could be called sensory surveillance. I don't have a lot of time to go into any details, more theoretical details, but what would be the characteristics of such surveillance that are important when we later on think of further implications for privacy and regulation more broadly that might also apply in this day-to-day context of our everyday life, not just, for instance, the military context. So we see that there is already, with all of these sensing technologies, an explosion in the volume of sensor-generated data. So again, even more data. Quantum sensing will bring even more data. And what I think here is very important is what is being measured and who is being tracked. It's not really individuals in most cases. It's some sort of type of environmental data, what I call environmental data. It could be something about, gravity. It could be the speed. It could be, we're looking at weights. We're looking at subtle differences. So it's not really, the focus really isn't some sort of individual or group of persons. So we are really, what this type of sensing technologies make is possible to measure additional things. And of course, now that we have this deluge of data, it leads to the further development and application of data mining and machine learning technologies to sift through them, because we have to now put them to use. We have to make something out of it. And again, how this sensory surveillance operates is, because we have all of these sensors out there, this surveillance is pervasive, it's always on, and it also is a passive type of data collection. So we are not involved here in any sort of active way. We don't even need to consent to data being, let's say, personal data, and that's the key question here, the money question, being gathered. The sensors are just out there, and they are sensing and storing all sorts of various data that are out there. So these are these key characteristics that are important when we think about, well, what kind of power does this sensory surveillance then lead to, that I call now sensory power? So we see a few shifts, and I've already mentioned them. So most of the time, again, when we talk about surveillance and privacy law and also data protection law, it's really about tracking individuals. An individual needs to be singled out, or at the most part, it's certain groups of people. This is now not really the main focus of sensory surveillance, because it can offer untargeted, non-systematic, very opportunistic forms of surveillance, okay? So the goal, and this is where I rely on surveillance studies scholars Mark Andreevich and Mark Burden, who said the goal of sensory surveillance is to capture a specific dimension of activity or behavior across the monitored space. So like I already said, we see this proliferation of sensors, and nowadays we just sense, therefore we surveil simply because it's possible. More and more is possible, so we sense more and more. So it's not really about specifically you or me. It's really a comprehensive portrait of a particular population or a whole environment or ecosystem, okay? So we get this big picture, and it makes me think of this notion that has been very popular for a while of digital twins, right? And now people are incredibly busy trying to even dreaming about making a digital twin of the whole world. And this is where this type of sensing technology ties in. So we see this shift from a relatively exceptional and discrete character of monitoring or surveillance to the monitoring of to a monitoring infrastructure which allows for passive, distributed, always-on data collection. So in this sense, advanced sensing technologies lead to an explosion of sites and opportunities for surveillance. And to finish off, this has important implications for privacy in a broader sense, and privacy and also data protection more specifically, because obviously new sensors open up new dimension of the population or a whole environment to sensing. And I've already said, even if individuals are not the focus of these sensors, of the data that they collect, when you put all of these things together, they can, of course, become the target of surveillance. And already once this big picture of an environment is created, this can be the foundation to zoom in and to start focusing on specific surveillance of individual. And in this sense, the conventional understandings of privacy as control over one's self-disclosure and also of data protection as control over one's personal data don't really suffice to protect us from this type of sensory surveillance and what it enables us to do. And I found it prescient that Andreevich and Burden, these surveillance scholars, in 2015 already wrote, increasingly, all data need to be treated as personal data in a sensor society. I found it really beautiful to see this connection of surveillance scholars, surveillance study scholars, having the exact same debate that we are having right now in data protection law and privacy law, where we see that these distinctions between personal versus non-personal data, or sensitive versus ordinary data, or metadata, and versus content of communications start to break down in the light of new technologies. And I'll leave the rest, I think, for the discussion. Thanks very much.
Thank you so much, Masha. Just, I have a very quick question, so also connecting with Chris. Is it, if advanced sensing systems are already quite pervasive and invasive, is it relevant to talk about countermeasures that Chris emphasized?
Oh,
About,
well, I have an idea actually about countermeasures, and it's a practical consideration, and it's something that surveillance scholars have already pointed out, and most famously by Latour, who talked about the fragility of surveillance. And I appreciate how Philippe already mentioned the challenges of implementing quantum sensing technologies in practice. So no one is arguing with Henning that the technologies don't work. Yes, they work and they are here, but in practice, even the slightest issues can make them break down. And this is what we see in general with surveillance technologies, that in practice, a lot of the things don't work. Smart cities haven't really lived up to their promises, I think, as many other types of similar surveillance technologies either. So we see they can easily break down in practice. It's very fragile. Surveillance is fragile, quantum sensing technologies are fragile, and in a way this is a practical sort of countermeasure that, thank goodness, it never works perfectly.
Thank you.
Maybe I have
go ahead. Please.
Well, your three talks actually raised a question, so it's a naive question, but so I agree with you. I mean, a lot of our sensing world today works because we have many sensors and they talk to each other a lot. Sometimes it's the same type of sensor. I mean, my iPhone is not very good in finding my position, but because there are many iPhones and they talk to each other, then it's actually very good. So from your talk, it seems to me that there is some kind of natural protection to the individual being today, is the fact that if you isolate yourself from the crowd, then you cannot be detected or not very good because your soul sensor is not very good. This is where the quantum sensing is making a paradigmatic change, I think, because if I happen to have like a single, like a super nice position navigation and timing device, which is not drifting and perfect, then I can single out one iPhone and then know exactly that this iPhone is there and does not rely on the other thing. So am I wrong to think this, or?
No, I trust you on this completely. What I do think is it's also a matter of question of deployment of this technology, in which contexts and at what price.
Yeah.
And this is something we'll have to see.
Great, thank you for this discussion, it was great. And before I open the floor for questions from the audience, I was wondering if any panelists would like to have a final comment on what has been said so far.
I had mine.
Okay. All right, great, then please feel free to ask questions, yeah, please. Yeah.
Thank you. Hello, my name is Laura. Thank you so much for this wonderful broad landscape of where we are in quantum technologies and the challenges and issues at stake. I was wondering if you all have had a thought on what should be kind of the policy framework for addressing or balancing, on the one hand, reaping the benefits of quantum technology and really help support different fields, especially healthcare and governments as well, but also to address the challenges that Professor Massa, I suppose, presented, as well as Chris. So for all of you, what do you think where are we in terms of policy frameworks, and what else is needed? Thank you.
Chris, perhaps?
Do you have a technical advice?
If I want to answer on the technical side, I would say the sensors can be better and better. This is true, and probably you get more and more information, more and more details. So the real problem lies on what do you do with the data, and how do you personalize the data in a certain way. I mean, it's and I think that's where the risk is. I mean, if you have like a precise map of a person, and then you can make the evolution of it, and then you have trace of it, then you know everything about someone. So this is really about how do you handle the data. I mean, I would say, but that's my maybe a scientific side, you cannot prevent evolution of like the technology. It will get better and better, so you just have to embrace it, and then you really have to say, okay, how will I use the outcome of this technology? And that's really about data, that's really about how you, the point you raised about surveillance and etc. But that's my feeling.
In the US, there's already a framework to deal with sensing into the home. So there's a precedent written by Justice Scalia in a case called Kylo. It involved heat emanations from a home and measuring the heat to see if there is a marijuana grow inside a home. And the Supreme Court in that case said that sufficiently advanced sensing technologies that could peer into a place where someone has an expectation of privacy that were not widely available require a search warrant. So some of the things I discuss would require a warrant if you wanted to focus it on someone's home. But let me add 2 levels of complexity to that. Law enforcement is not going to have these technologies soon. It's actually going to be militaries and intelligence agencies. So we'd want to think about different or maybe no regulation in those fields. Then switching to a day where law enforcement could use this, one of the hypotheticals we model in our book is concerns probationers and parolees. So people who have been convicted of crime and they're released to their home, agree by contract to have a lower expectation of privacy. So how about, could we imagine a future where there's a gravimetric sensor that's mounted on, let's say, a UAV, and on its daily routine, it flies over the homes of people who are on probation and parole to detect whether they have guns in their homes? Those are the types of the scenarios that we could foresee that could possibly be compatible with existing privacy law, and yet very privacy intrusive.
Thank you, Chris. And also to add to that, so you also mentioned like remote sensing technologies, and this could target people in public spaces as well. So then in Europe, there is we also care about privacy in public space, and maybe Masha would like to say something about that.
Yeah, well, we already have a bunch of case law from the European Court of Human Rights on privacy in the public sphere, and that includes also public spaces. So we do have, to put it more in US terms, expectations of privacy also in public space. And we, of course, have the data protection framework that deals with any type of collection of personal data, no matter where this takes place, right? The problem that I was also trying to raise in my talk is that a lot of the sensing that is happening now with advanced sensors is potentially non-personal data, and is considered as such with a lot of, for instance, smart cities, other types of projects. So then the idea is, well, then data protection law doesn't apply, and then in a way it's open for anything. So that's a bit the issue that we are running into here on these distinctions between different types of data, whereas they still enable potentially intrusions into people's privacy. And that's where the law starts to break down.
Thank you, Masha.
Yeah.
Are there any other questions?
Yeah,
Please.
it connects what you already asked, a bit more on the technological side, meaning that at the level of precision you were talking about in terms of sensing, how do you see the future of remote identification and fingerprinting at the end of the day of individuals? I have the impression that this kind of technology might reduce to zero the possibility of false positives in this kind of sensing, whatever you want to consider as a complementary to facial recognition and other kinds of biometrics, or in itself alone. What can you say about that?
Yeah, well, I have an example to your question. Is I bumped into an entrepreneur who started a company where he's taking a picture of the vein structure of your hand. And this is providing a much better identification than like a fingerprint or anything. So that's exactly what you say. And then the question is raising about, and this is where Europe and the US are very different actually, because again, it's about data. I mean, so I do believe that better sensor will allow you to get a description of a single individual in a much better way, or like maybe a unique way, like with no false positive. If you combine weight measurement in a certain way with, I don't know, like heartbeats, like a map of your heartbeats over the whole body will be very different from one person to the other, even though the heartbeat itself will look the same. So this is the kind of things that can lead to a real discussion about privacy. But again, it's good for health, but then you need to be very sure that it's not used for it's good for authentication as well. Every person can be identified, but I forgot what this person told, but there's really a question about whether you identify the person or whether you like store this person as a single individual, because it's good for this person to be identified as a single individual for accessing the bank account, for accessing all these things. And there is I think the boundary is very thin between the two things.
Thank you. Any other questions from the audience? Yes, please.
Henning, I was curious about the projections that you have mentioned. Do you think that for the cases, especially for the sensitive hardware where the precision is required, scalability and ease of complexity, let's say how to make it easier to deploy. So do you think that market analysts have looked at two factors? And before I leave, question to Masa. Masa, you just mentioned that we have already a lot of advanced sensors, and they are already a lot of collecting data, but we are not sure, potentially they are not collecting personal data. But do you think that legal, usually in the law, I'm not a lawyer, I'm a technologist, so I'm very excited about the technology. In the law world, there is a sentence that law is always behind technology. So when I look into your talk, it looks like, okay, we shall not worry about this at this moment, but let's wait. So usually when we talk about AI Act now, so do you think that, okay, after 5 years, when we see the technology is coming to public life, now it's no more internet, it's no more military or it's no more hospital, but it's touching public life, it's touching individuality. Now let's talk about quantum law. So I'm curious about that. Thank you.
Was there a question for Henning? No?
Maybe you go first, and then I do my part.
I do have an answer to this. Yes, I mean, that's a very known maxim, right? The law is always lagging behind, and I'm sure there's always truth to this type of thing. On the other hand, you mentioned the AI Act. You know, there are numerous types of laws and fields of law that already regulate AI technology. And if those laws would actually be properly taken into account and respected, AI would already be nicely regulated. So that's actually my opinion on that. But sometimes the law doesn't work in practice, and sometimes we need a nice, hyped new law to come up with that maybe someone will start listening to. But let's not forget about the other fields of law.
Yeah, but that is the problem in Europe we see usually in the legal field, that let's make a new law to make it hype, as you just mentioned.
Yeah.
Then maybe just concerning also the question in terms of the scalability. So scalability is one of the key challenges that we see in terms of also the uncertainties that we have in terms of what is the overall market size. So this is one of the key determinants as part of this. The other is, in addition to scalability, of course, that if there is also the monetary question in terms of how much these devices at the end would also cost, because in many cases currently we would rely on rare earth metals, or sort of what you were also referring to in terms of massive cryogenic devices. Okay, like this is not something that we can easily affordable in a typical home. So number one, what we have considered is what is a rough projection then also on the technological progress that we would see also based on past experience. What we currently see also with the recent announcements that you would have seen also around the technology, also making the first at least halfway fault tolerant quantum machines in the first place, we see that actually the acceleration of breakthroughs that we see in terms of getting to scalable devices is on a faster pace than we would have originally anticipated, which is, I think, good news. The final point that I would like to make on the scalability question, then that is why I also referred to the ecosystem question, is we think that a lot of the challenges that we also see in terms of the scalability of the solutions, for example, if we look at magnetic field sensors on the Earth, I don't need to have for every oil company a massive array of quantum gravity sensors everywhere around the entire world in order to measure the magnetic field, in order to identify where there could be like possible sites for oil exploitation. We believe if we would basically be able to connect the data that we would have in terms of the exact gravity that we would have on the different places on the Earth, we would be able to identify through the ecosystem of those sensors at a much lower cost what would be the interesting sites for oil drilling, or possibly, of course, also for other materials that you could also identify through the respective measurements. So the simple answer is taken into account, again, sort of with the caveat that we always have to make, there are certain unknowns that we have there. If at some stage or another suddenly sort of there is room temperature superconductivity, which I don't assume that will exist in my lifetime, but hopefully I'm wrong. If this suddenly would come along, it's a game changer, let's face it, and then sort of we would need to reevaluate. Second is, we believe that a lot of the scalability challenges can be overcome if we would have this ecosystem also of sensors that would be able to overcome those.
Thank you, Henning. Well, we are almost out of time.
Hi, I have the
but
mic
we can take
already.
one short question. Yeah.
Hi, thank you so much. Regarding also like this hype that we have with AI and predicting future all the time, I would like to know how quantum sensors are connected with present or with future, if they are connected with any kind of patterns regarding prediction, or if it's something that is more like in real time, present time.
I'm not sure I get the...
Do you want to start, or should I start?
Yeah, can you
Maybe you give it a go, and then
Can you repeat the question? I'm not sure I...
Yeah, like we have this hype right now
Uh-huh.
with predicting the future all the time.
Yes.
So my question is like quantum sensors are also something that are based on like present, or is something that people will try to use to predict future things?
I think it's both. So in one way, if you want to... the example of gravity is a good one. If you want to predict the future, you need to know what's happening now. It's very important. And then another nice example, it's the weather. I mean, to make a weather forecast, you need to know what is the weather today. And it's a very funny thing that happened about sensing, actually. It's today the weather forecast is much worse than before the pandemic, because during the pandemic, the plane did not fly, so there were bazillions of sensors that were missing in the models, and then you need to rebuild the models, and that's a very interesting example about how a sensor can actually make a difference into your production of the future. So quantum sensing, as of today, they are not providing data in or they are just starting to provide data in a usable way, because they are just at the very beginning. But we are preparing. I think there are lots of studies made. There are lots of programs. The EU has launched a few programs really to, like space surveillance and etc., that are actually preparing these sensors to give the data that will allow us to get better knowledge of what's happening today, and then from that make good predictions about many things like water management, resource management, I don't know, ice melting and everything. Yeah.
Henning, did you want to add some? I mean,
No, I just think sort of
30
one
seconds.
addition that I think is worth is specifically in terms of this prediction of the future. Sort of one thing that is definitely new is the whole advent also of generative AI as a new method also for doing future predictions. And sort of one of the things that we've not yet fully explored is definitely what can we do also with all of the sensor data that we would have available, also with generative AI, because for example, we would be able to reconstruct, okay, like if we have a lot of sensor data on the person, like what would be like the outer appearance, for example, that we could also deduce from the respective sensor data. Would we be able to, for example, predict how this person will be aging then also going forward? So there are a lot of new use cases and possibilities that could possibly be out there that we've not yet fully explored also to the full extent. But definitely this is something that is completely new that is also coming. Interesting to see that also generative AI has a downside in terms of it consumes a lot of our compute capacity at this point, and also quantum computing might be a possible resource in order to provide for the respective capacity needed for model training and similar aspects. So I think this could be this is a nice area of future research, and there could be a lot of additional benefit also from bringing together the new technological developments on the AI side as well as also on the quantum side.
Thank you so much. We really have to wrap up. We're all out of time, and I'm really happy that there are so many people interested in quantum sensing. I'm glad that you came, and thank you for the panelists. It's like an amazing panel. Thank you, Philip, Henning, Chris, and Masha. Thank you for all the insights, and enjoy the rest of the conference.
Thank you.